Hey everyone, and welcome back to another explainer from Forge College. I am absolutely pumped to be your host today because we're hitting a really crucial milestone in our journey. Just to give you a quick map of where we're at, we're diving deep into the from EVM to SVM track. More specifically, we're navigating the advanced ERC patterns on Solana course, right smack in the middle of the ERC 4626 tokenized vault module. Today's topic? It's a real game changer. We're talking about the AI accelerated refinement of vault logic. We're essentially going to take that raw basic machinery we built last time and transform it into an absolute tank of a financial engine. And the best part? We're bringing in AI to do the heavy lifting with us. So one tiny math error can empty a Web3 vault overnight. I know. It sounds like a tagline for a horror movie, but honestly, in the world of smart contract development, it's just reality. You probably remember from our previous lesson, building a minimal Solana vault, guided build, that we successfully laid down the foundation. We got the basic deposit and withdrawal handler logic working, we initialized accounts, we minted receipt tokens. It was awesome. But here's the catch. A minimal vault is an incredibly fragile vault. If you leave even the tiniest division by zero loophole or just a slight rounding bias in their share price conversion, poof, your users' funds are totally gone before you can even pour your morning coffee. All right, let's quickly run through our engineering blueprint for today. We'll start with the fragile basic vault, then move into the vibe coding cycle. After that, we're nailing the fee logic, picking a rounding strategy, and aggressively testing edge cases, all leading up to getting ready for the audit. Let's jump right in. Part 1, the fragile basic vault. Let's really understand the danger we're dealing with here. Now, why exactly is leaving our vault unrefined such a massive disaster waiting to happen? Well, taking assets and handing out shares is a breeze when the math is absolutely perfect. But the blockchain? It's chaotic. Users out in the wild don't just deposit nice, clean, round numbers. They deposit weird fractions, micro amounts, and they trigger these crazy edge cases that can literally detach the value of your shares from the underlying assets. Think about the stark contrast between our minimal vault and a refined one. The minimal vault does basic minting and burning. It's kind of like an engine block just sitting on your garage floor. Sure, it fires up, but there's no way you're dropping it into a race car. The refined vault, on the other hand, demands robust accounting, highly precise fee handling, and rigorous edge case testing. We have to transition from a setup that mostly works to one with the surgical precision required to stop a tiny rounding error from draining millions in liquidity. Moving to part 2. The vibe coding cycle. It's time to meet your new AI mentor. Look, writing perfect, integer-safe Rust accounting math totally from scratch is tedious. Actually, scratch that. It's completely headache-inducing. And that is exactly why we're bringing in an AI assistant to act as our ultimate tireless coding mentor. It never needs a coffee break, it never gets frustrated with us, and it can churn out and refactor super specific mathematical routines in seconds. We execute this through a really specific 3-step vibe coding loop. Step 1, you ask the AI for a small, isolated piece of code, like say a function just to calculate fees. Step 2, you immediately run highly focused unit tests locally on that exact snippet. And step 3, when a test fails, and believe me, it will fail at first, you feed that exact failure right back to the AI and refine it. This loop keeps our refactoring small, atomic, and most importantly, incredibly safe. We aren't asking the AI to architect an entire protocol for us. We're just asking it to perfect one tiny mathematical gear at a time. Okay, part 3, nailing the fee logic. Basically, who gets paid? So, armed with our AI mentor, we're ready to face our first major trial. Vaults aren't charities, right? They need to collect fees to keep the lights on. But making sure our vault properly tracks and distributes those fees without causing a total arithmetic panic is surprisingly tricky. Just ask yourself, when a user deposits 100 tokens, do you scrape that 1% fee out of the 100 underlying tokens first, and then calculate their shares? Or do you calculate the shares they'd get for all 100 tokens, and then take the fee out of the newly minted shares? That order of operations fundamentally changes the math, it changes the rounding, and ultimately, it shifts the entire economic balance of the vault. To solve this headache, our fee accrual mechanism has to preserve absolutely strict integer safety. This is exactly where we lean on our AI to separate concerns. We prompt it to write tiny, completely isolated Rust functions like a standalone apply fee function. By walling off this logic, we guarantee that our total value accounting stays pinpoint accurate, no matter if we're using a fee on transfer model or a periodic accrual model. Next up, part 4, picking a rounding strategy. Welcome to the precision trial.
Because we only ever deal with integers on the blockchain, dividing odd numbers always, and I mean always, leaves a remainder. How you choose to handle that little leftover piece is one of the most absolutely crucial architectural decisions you are going to make. So let's weigh the trade-offs of the three main rounding strategies. If you go with floor rounding, you're always rounding down, it's super conservative, and make sure you never issue more shares than you actually have assets for, but it does leave tiny dust residues just sitting in the vault. Then you have ceiling, where you always round up. It's very generous to the user, sure, but it can slowly, steadily dilute the vault's overall value. And finally, there's bankers rounding, which is tie to even. It's a neutral approach and drastically reduces systematic bias over thousands and thousands of transactions. Your goal is to use your AI vibe coding cycle to implement all three, test them rigorously, and consciously choose the exact one that fits your vault-specific economic model. Now, please read this carefully. Internalize it, print it out, and tape it to your monitor. Always use integer arithmetic. Never, ever use floating point. I really cannot stress this enough, folks. Floating point math on the blockchain is an absolute horror show of non-determinism. We have to rely strictly on explicit, integer-safe helpers. When you are prompting your AI, you literally must demand that it uses checked underscore mul for multiplication and checked underscore div for division. That is the only way to prevent those terrifying runtime panics.
Part 5. Testing the edge cases. Let's try breaking the vault. So, we've written the logic, we've locked in our rounding strategy. Now it's time for the final trial. We need to intentionally try to break this thing. We have to throw the most pathological, chaotic scenarios imaginable at our AI-generated Rust routines just to see if they hold up under pressure. There are 4 specific edge cases you need to prompt your AI to test. First, the initial mint path. What exactly happens when a user deposits into a completely empty vault that has 0 total shares? The math behaves very differently there. Second, microdeposits. What if someone deposits exactly 1 single unit of an asset when the vault is already holding millions? We have to ensure that one tiny deposit doesn't accidentally trigger a structural bias or a division by 0 panic. Third, we test fee extremes, everything from 0 fees all the way up to 10,000 basis points, which is a 100% fee. And lastly, we test for those sneaky rounding-induced residuals over thousands and thousands of iterations. Finally, part 6, ready for the audit. The reward phase. If you've iteratively run those edge case tests, fed the failures back to the AI, and refined the code until every single test is glowing green, massive congratulations. Your code is no longer fragile. It is modular, it's properly documented, and it is mathematically hardened. You see, the ultimate unbreakable rule of vault accounting is this: a deposit and an immediate withdrawal must return to the exact original asset count. If we ignore fees for just a second, this concept is known as the round-trip invariant. It's the core mathematical contract that actually guarantees your users' funds are fair and secure. If your unit test can definitively prove that this invariant holds true, you have successfully built a genuinely robust accounting module. And right there is our victory condition: a modular, thoroughly tested, and completely integer-safe math module. You've successfully used AI not as a crutch, but as a hyper-focused partner to drastically accelerate the refinement of your vault logic. I highly encourage you to head over to our website, forge.college, to dive much deeper into these exact AI prompts, grab the code snippets for yourself, and learn more about advanced ERC patterns. Also, definitely keep your eyes peeled, because these exact hardened routines we just built are going to be absolutely crucial for our upcoming lesson on auditing and debugging vault implementations. Before we wrap up, I want to leave you with one final kind of provocative thought. If your rounding strategy systematically biases by even a tiny, microscopic fraction every single block, who eventually owns the vault over a long enough timeline? Seriously, think about the slow, silent bleed of an unrefined contract. It's a fascinating economic puzzle, and it is exactly why the extreme precision we learned about today matters so much. Thank you all so much for joining me on this explainer from Forge College. Keep learning, keep building, and I will see you in the next one.